So friends, welcome to our channel. So today now we are going to discuss a question of column from RCC. Now the question here is, design a short RCC column to carry an axial load of 1600 kilonewton. It is a 4 meter long, effectively held in position and restrained against rotation at both ends. Use M20 concrete and Fe415 steel. So these are the given proportions or given values here. So from where can we start? So now from here we can take that its length is, the tail is 4 meter. We can assume that, not assuming, this value P or load, that is 1600 kilonewton, and obviously we know from that FCK for M20 concrete is 20 Newton per mm square. The FCK we all know that characteristic compressive strength of concrete, and Fy, the characteristic strength of the steel, here is 415 Newton per mm square. It is given up here. Now here the thing that is given here is, it is long effectively held in position and restrained against rotation at both ends. So from here, if we want to get the effective length, so you can get it from IS 456 code 2000, that is the annexure is E annexure, and it is of clause E3. You can get it from there, that for this portion we get L effective equal to 0.65 of the length, that is the length given here. So we can calculate it 0.65 into 4. So it actually comes, if you calculate, it actually comes 2.6 meter, or you can take it as 2600 mm. So we got here that L effective. Now we get to the second step. The second step is the factored load here. So we can write it here, the factored load, which is been symbolized as PU. So we can take it at 1.5 of P, that is the given load up here, that is 1.5 into 1600. So it comes 2400 kilonewton. So we got the factored load. Now here we have to calculate the percent of steel. So it is not given up here, so we can assume it, that assuming 1% of steel. Actually this is all from the IS codes, that you can actually assume it 1% or 0.8% of steel. So I am assuming here that 1% of steel. So that becomes, this is the area of steel, actually ASC, area of steel, that is equal to 1%. So 1% of what? That question comes to your mind, that 1% of what? 1% of AG. 1% of AG means the gross area. Actually it is taken as 1% of gross area. Gross area means that total length, it is covered up by the concrete and everything. So from 1% we can only take it 1 by 100 of AG. So we can take AC as 0.01 of AG. We can take it 0.01 of AG. Now what comes is the main equation that is required to design a column. The main equation that comes up is PU, that is the factored load upon here, is 0.4 of FCK into area of concrete plus 0.67 into Fy into area of steel. Now here that is given up, that I got this area of steel, but which is unknown to me is the area of concrete. So we can take it that area of concrete is equal to that gross area minus area of steel. Gross area minus area of steel, we can get it. So if you take that AG, and we know that AC is 0.01 of AG, so we can, from here we can actually take it as this, like so it actually comes of 0.99 of AG. So I got AC here upon, so I can put it here. I got the PU value, the factored load value, that is 2400 kilonewton. 2400 equal to 0.4, that FCK value we know here upon 20 Newton per mm square. The AC value we got here 0.99 of AG plus of 0.67. We know the FY value, that is 415, and we know the ASC value, that is 0.01 of AG. Now from this calculation actually all that is, this is given up here, that is in mm, that is all are 415 mm square, Newton per mm square, 20 Newton per mm square, but here it is 2400 kilonewton, so we will change it in Newton to 2400 into 10 to the power 3 we get. Now we can write this equation as like this. Now from here we can get the value of AG. The actual value of AG, if you calculate, it will come as 224,299 mm square. So this is the AG value. Now we didn't get the dimension, that what is its length, what is its breadth. If my question is given as like 400 into 500 or 500 into 500, then that's another type of sort of question, but here it is not given, the dimension is not given. So from this one you can get the dimension, that is if you calculate that, it you can root under this value to calculate the dimension. If you root under, actually I am giving the approximate, not approximate value, I am giving the closest value, that it will come around something 500. So we can assume that this is 500 into 500 mm dimension of column. So we get here. Now what is the main important thing upon here is the slenderness ratio. So what do you mean by slenderness ratio actually? So if you write the slenderness ratio here upon, actually slenderness ratio is effective length by its breadth. So the term come out here that if we get this L effective by breadth value less than 12, it will be a short column, and if we get the value L effective by breadth greater than 12, then it's a long column. So you have to know this, these values differ for this. Now L effective, what I got, that effective length, we all know the effective length is given here 2600 of mm, so I am writing it here 2600 mm divided by its breadth. Now I have got this length into breadth. Actually if we take this all our length and all our breadth here upon, so 500 is to 500, so I got this, so it's divided by 500. Okay, so what we get is the value is 5.2. Now 5.2 is obviously less than 12, so we can conclude that it's a short column. It's a short column. Now what the next steps come is the eccentricity part, the minimum eccentricity. The minimum eccentricity, that is E minimum, and we all know the formula, that is given up by L by 500 plus D by 30. Now effective length we got here, that is 4 meter, not effective length, the original length of this, that 4 meter long column, so we got it 4 meter, so we can write it as 4000 mm, so we can take it as 4000 by 500. Now D, what is D? D is this length, breadth or depth, you can conclude is a breadth or depth. So this is the depth, 500 is to 500, so 500 by 30. If we do this calculation, then we get minimum eccentricity as 24.67 meter. Now here it comes that E minimum by D, E minimum by D should be E minimum by D, actually this comes that E minimum by D If it comes less than 0.05, then it is an short column of axially loaded. So we have to share it there that E minimum we got 24.67 and D is my 500 value, and this comes as 0.049, which is less than 0.05. So we can tell that it is designed as axially loaded short column. Now the next part comes is that area of steel. We have to calculate the area of steel. Now area of steel actually is given that from here we can get that area of steel, this one 0.01 of Ag. So if we calculate that 0.01 of Ag, so it is given up there 0.01, and we all know the gross value up here, the gross area value, so we can write it 224,299. So we get the value as 2243 mm square. This is the area of steel. Now what the thing comes that you have to assume the bars needed to make the column, to design the column. You have to assume that. So I am assuming up here that it is a 20, we have given up 20 mm dia, bars of dia 20 mm we have given up here. So the area of that bar should be, we all know, pi by 4 of d square. So here it is 20 square, so it comes as 314 mm square. Now number of bars required, the next steps come is the number of bars required. So how can we get the number of bars required? We got the total area of steel, and if we divide the total area of steel by area of this one bar, we can get the total number of bar. So ASC by, if we take a Fi, so 22 upon 43 divided by 314, we get it nearly compared to 8. So we provide here 8 bars of 20 mm dia. Now this design is almost completed. The next part comes is the lateral ties. Now the lateral ties is that 1/4 of its dia of this type of columns. So 1/4 of dia is given up here 20, so 5 mm. So this is given. So pitch in the ties is not exceed of the following. So least lateral dimension, that is the least lateral dimension we get here is 500 mm. From this, actually we conclude this from this dimension, that it is an 500 is to 500.